Okay, today we're going to be finishing up chapter 1 and talking about the beginning of chapter 2, focusing mostly on frequency and graphs related to frequency. Before we do that, however, we want to talk about one more level of measurement type talk, finishing up the key terms discussion from last time. Similar to the types of data and types of variables we talked about last time, we have one more way to categorize data in terms of the level of measurement. And there's 4 different levels of measurement that we can discuss: nominal, ordinal, interval, and ratio. This categorization of data is particularly important because it deals with the types of analysis that we could possibly do. The higher the level of measurement, which would be indicated by being a lower number down here, the more possible analysis we can do because there's more that can possibly be extracted from the data. Now, the first type of measurement is nominal. Nominal is basically the categorical or qualitative that we've discussed before. There's no numbers, no order to possibly put it in. It's just categories of things. Favorite food or identification number, things like that. There's no possible way to put the data in any meaningful order. The next type of data would end up being ordinal. Ordinal data can be put in a certain order, but you can't make any meaningful statement about what the difference between different data points would be. For example, suppose I said, rate this movie on a scale of 1 to 10. If I said that my movie, I thought the movie was a 3, and you said the movie was a 5, the difference there is 2. But that difference being a 2 doesn't have any real meaning. It doesn't mean that the movie was 2 better. You can't really talk about what that means because the difference between a 1 or a 3 or a 5 or whatever doesn't really have any meaning. This data could also be things that aren't even numerical, as long as you can put it in order. For example, when you're taking a poll and it says agree or disagree, maybe it says strongly agree, strongly disagree, that would be an instance of ordinal data because you can put it in order from least agree to most agree. But the difference between levels of agreement doesn't really have some significant meaning. The word for that kind of scale is a Likert scale, and it's very commonly used for polls today. One step up from ordinal data is interval data. Interval data can be put in an order, and this time the difference between data points will have some meaning. For example, if I'm talking about the time of day, we can say that I arrived at 3 o'clock and you arrived at 5 o'clock. It's meaningful that I arrived 2 hours earlier before you did. You can talk about the difference between different times of day. However, the ratio of different times of day doesn't mean anything. For example, if I arrived at 3 and you arrived at 6, you wouldn't say that you arrived twice as late as I did. That doesn't have any specific meaning. 6 o'clock in the afternoon is not twice as much time as 3 o'clock in the afternoon. And so an interval data is one where the difference between data has some meaning, but the ratio does not. In other words, you can talk about something being more than something else, maybe being 2 more, but you couldn't talk about it being maybe twice as much or half as much. If you have that kind of thing, that's when we're talking about ratio data. Ratio data, which is most of the numerical data that we will possibly be working with, does have meaningful multiplication and division. For example, if we're not talking about the time of day, but instead the time elapsed, maybe I was 3 minutes late to class and you were 6 minutes late to class. Well, now you can say that you were twice as late as I was. The fact that your number is twice as big as my number has a meaning. And so that would mean that we have this ratio number being significant. So in other words, you can think about for each data something extra that you get. When we go up to ordinal data, what you get extra is an order. Then from going from order to interval, what you get extra is a difference. And then going from interval to ratio, what you get extra is a ratio. If we think about the difference as the interval between 2 points of data, then all of the bottom 3 names of categories are very easy to remember. The top one, nominal, is the only one you'll have to remember. Alternatively, you can think of nominal kind of like just a name. You have a name of something. It's not a number, it's just a name. Nominal, then ordinal, then interval, then ratio. Now that we've finished up the different types of data, we've wrapped up the main key terms discussion, and we can actually start looking at some specific sets of data. We're first going to talk about frequency. Frequency is simply counting up how much a type of data occurs. This is the most basic level of analysis that we can do. Give out a survey, do an experiment, and gather some data. Count up how many times each response happens. Frequency is the number of times that something happens. Often, we'll care more about the relative frequency than the base level frequency. Relative frequency is the ratio of the frequency of a certain data point to the frequency of the entire sample. So if I sample 30 people and 6 of them answered in a certain way, then the frequency would be 6, and the relative frequency would be 6 over 30, or 20%. And it's okay to leave it as a fraction or to leave it as a decimal. So oftentimes the decimals don't round properly, so I'm going to work primarily in fractions just because it will look a little bit nicer, and we'll maybe go to decimals for some of the analysis, but just for recording things, fractions will end up working nicely. Cumulative relative frequency is the same as relative frequency, except instead of just counting up for that data point, it's for all of the data points up to and including our data point. So for example, we might say, I'm going to count up all of the people, instead of the people that responded 4, I'm going to count up all the people that responded 4 or less. This will be cumulative relative frequency. It only makes sense to talk about in terms of ordinal data, because if there's no order, then we can't talk about what came before. It would also work with levels higher than ordinal, so interval or ratio, but it has to be at least ordinal. Nominal won't do. Now that we've got this idea of frequency, we can actually start discussing some different types of graphs. Let's take a look here at this data gathered by a researcher who's establishing the effectiveness of a certain AIDS drug in very severe cases. After applying the drug to the different cases, they measured out all of the different data for how long the patient lived in months. We're going to fill in a frequency table based on this data. So the first thing we'll notice is that the frequencies have been grouped here into different categories. We're going to talk more about this later on in the video, but for now, just know that very frequently it makes sense to group data up in order to make a graph or a table easier to read. So the first thing we're going to need to do is we're going to, for the frequency column, tally up the number of data points that were recorded in each category. For the first one, we're looking for everything that is between 0.5 and 6.5. And the reason that we have it from 0.5 to 6.5 is that there's no question as to where 6 would fall or where 7 would fall. We put a decimal as the break point between the two different categories so that we don't have to worry about whether we include a whole number in one category or the next. So let's just go ahead and tally it up. I see 1, 2, 3, 4. Oh, whoops, sorry. We shouldn't be including these 8s because we're only going up to 6.5. So 1, 2, and that's it. 2 for the first one. Next, we'll do from 6.5 to 12.5. So maximum will be 12. I count 1, no, 2, 3, 4. 12 is included. 5 for this next one. Okay, going up to 18.5. 1, 2, 3, 4, 5, 6, 7, 8. The next one up to 24.5. 1, 2, 3, 4, 5. This one should actually be in the last one. So let's box that so we don't forget. So 5 here. And then this last one needs to go up. We put down 8. It should have been 9. And we can cross out that 18. Next, up to 30 will be the highest. 1, 2, 3, 4, 5, 6, 7. 36 will be the highest. 1, 2, 3, 4, 5, 6, 7. 42 will be the highest. 1, 2. And then 48 will be the highest. 1, 2, 3. We can check and look to make sure we haven't missed any data, that every number got crossed out. It looks like we are good. So this is the frequency. We just counted up how many times each thing came up. Now we'll look for the sum. This symbol right here means sum, and it's counting up the total. So the total frequency, 2 plus 5 is 7, plus 9, 16, plus 5, 21, plus 7, 28, plus 7, 35, plus 2, 37, plus 3 will be 40. So for each of the relative frequencies, we're just taking the given number and putting it over 40. And this can end up being very helpful because now we can look at the proportion of the whole that we had. Let's also change these numbers into decimals. And actually for this one, because it's 40, it will end up coming out cleanly, so that we can get a good sense. So 2 over 40 is going to be 5%. 5 over 40, 12.5%. We've got a 22.5, 12.5. This will be 17.5, and again 17.5, 5, and 7.5. So we can look at this data and we get a good sense of the proportion. For example, I see that 22.5% of people lived between a year and a half, according to this row of the table. Now, frequently we want to check how long people lived in a much larger range. Maybe we want to check, for example, whether people lived between 1 year and 3 years. In that case, we would need to add up all 4 of these categories. So I would do 9 plus 5 plus 7 plus 7. That ends up being 14 plus 14, which is 28 out of 40. And we can similarly add up the percentages and see that 70% of the people lived between 1 year and 3 years when in this given sample. The cumulative relative frequency is when we add up all of the numbers up to there. So the first one will simply be 2 out of 40, which is still 5%. But then the next one is 2 plus 5, which is 7 out of 40, which we know is going to end up being 17.5%. And then for each next data point, we're going to add the previous cumulative relative frequency with the next relative in order to get the sum up to that point. So for example, for this next one, we're adding the 9 to the 7, which is exactly the same as we would get as if we added the 9 to the 5 and the 2 that preceded it. So this gives us 16 out of 40. I'll fill in all of the percentages at the end. 21, then 28, then 35, then 37, and finally 40. It should always work out that the final one is 40 out of 40 or whatever out of the total. The total out of the total, it should end up being 100%. This makes a lot of sense because the cumulative relative frequency says, give me all of the values that are less than or equal to this value. And for the final value, everything should be less than or equal to it. We can fill in the percentages as well. So 16 out of 40 would end up being 40%. This will end up being 52.5, 70, 80. Oh, sorry, not 80 here. Oops. 82.5%. Then 92.5%. Oops. And then this last one is not 82, it's 87.5. Double check to make sure all the numbers are right up through here. Good, and then good. Okay, so now this gives us the cumulative relative frequency. And we can see that this gives us all of the numbers very quickly for up to a certain point. How many people lived at least 3 years, for example? Well, we can see that 87.5 people lived less than 3 years. And so that means that we can simply subtract and say that 12.5 people lived 3 years or more. You can use this to basically get a sense of how many people lived at a certain point and less or and more. Now that we've got this notion of frequency down, we can start talking about different types of graphs. The first type of graph we're going to look at is not really a graph so much as a visual way to write the data down. It's sometimes treated like a graph. It's kind of like a bar graph, but you'd write the numbers out rather than actually writing out a bar. The way you do this is you will fill in only the first digits. In this case, my first digits start at 0 and go up to 8. And then we will write down all of the second digits. So here, my second digits for 0, for example, are 5 and 7. For 1, I see 1, 2, another 2, 3, 3, 5, 5, 7, 7, 8, and 9. And then for 2, 0, 2, 5, 6, 8, 8, 8. It's important that you line the numbers up so that they're moving at the same frequency, because the whole point of this graph is to fill out and see how many data points have each first digit. And it's supposed to be a visual representation. For 3, I see a 5 and an 8, and that's it. Then I see 4, 8, and 9, 2, 5, 7, and 8. Then nothing for 6, nothing for 7. That's okay, but we still needed to write them. And then at 8, there's a 0. And this gives us a really nice visual idea of what's going on. We didn't look at what the type of data was. It says it's distance in miles from a student's home to the nearest grocery store. But if we think about there being bars here, it gives us a pretty good graphical representation of what's going on. Most of these students, it looks like, live somewhere between 1 and 3 miles from a grocery store. There's a good chunk of people that live 4, 5, barely 6 miles from a grocery store. And then there's one student who lives very far. Maybe this student lives on the outskirts of town rather than in the center where most of the students reside. Gives us a nice, quick, easy visual representation of some data. It's nothing special, but it's a very simple way to graph data. Let's take a look at some more detailed ways. We can make line graphs and bar graphs of data. For both line graphs and bar graphs, the idea is that the x-axis will represent whatever categories we're working with, and the y-axis will represent the frequency. We can use this for any type of data, not just categorical, but we'll be treating it for the purpose of analysis as if it's categorical. If our data was numerical and we're making a bar graph of it, then we're really just counting up how many times the data showed up. Make sure when you are creating your graph that you label your axes. So we might say, for example, that the x-axis will end up being favorite food, and the y-axis might be the relative frequency. We have pizza, ice cream, and burgers. And so this might be, let's do it this way. So let's say that this is 10%, 20%, 30%, 40%, and so on. Notice how important it is that I'm labeling my graph here. If I didn't put down these percentages, if I didn't label what each bar represented, then you wouldn't be able to know what this graph was about. Sometimes it's even important to give a name to the graph. So favorite foods of students. And then we can create a bar for each. Maybe 30% have their favorite food as pizza, 10% say ice cream, and 60% say burgers. Gives us a nice visual representation of what's going on. Now we could create the exact same graph as a line graph. Same deal, pizza, ice cream, burgers for favorite food. And then we've got the relative frequency, 10, 20, 30, and so on. I would say when you're labeling a graph like this, at least 2 values will be enough to establish your pattern on the relative frequency side. For the x-axis, since it's categories, you have to label them all every time, otherwise it doesn't make sense. But for an axis that goes by numbers, just make sure you label when making a graph by hand at least 2 points so that it's clear what the pattern will end up being. For a line graph, we would basically plot the exact same data, except we would put it down as dots and connect it with lines. Now, the issue with this is that it seems to indicate some kind of trend. It seems like we're flowing from pizza to ice cream to burgers. Doesn't really make a lot of sense for this to be as a line graph. As a bar graph, this is more telling. A line graph might be used better if we're trying to show some kind of trend. For example, let's suppose that I take the exact same graphs, same relative frequency, but instead, I'm going to change the x-axis to instead say first, or let's make it this way. So we'll say age, the first rode a bike. And we'll say 9, 10, and 11. Change the second graph as well. Now it makes sense to have a line graph because we're flowing from point to point. Okay, some students started at 9 and then it went down from 9 to 10, but then it went way up from 10 to 11. This data is now kind of flowing from point to point to point, and it makes sense to do so because of the type of data. Previously, we had categorical data, but now we've got this age data. Age is ratio level data, the best level that we can possibly get. And so we can see that in the first scenario, the bar graph made a lot more sense, whereas in this scenario, I feel like I'm pretty happy with the line graph. Sometimes it makes more sense to do one or the other. Sometimes it doesn't matter. The graphs still tell the same story, but because we are people and looking at pictures gives us different thoughts in our head, different types of graphs are more intuitive to line up with different types of data. And part of telling a really good story with your graph is choosing the right type of graph for the job. Bar graphs are a really good option for categorical data, whereas line graphs are really good for continuous data where you want to imply a trend. Now, the issue is that if I am taking my data from a large enough sample where we're actually going to be able to do math on it, then I might have 100 or more different types of data or different responses. If I'm taking people's heights, for example, I might expect that the heights would be anywhere from 4 feet to 7 feet would be a fairly generous range. There may be outliers beyond that. Most will probably lie from 5 feet to 6.5 feet, but they're going to be people taller and smaller than each of those endpoints. And so we need to make sure that we're accounting for that. And if we're measuring to the nearest inch or the nearest half inch, that's going to be way too many data points that we're going to want to put each one individually on its own bar. The way that we can account for this is we can group the data together. It only makes sense to group data, of course, if we're at least ordinal, because otherwise you'd be grouping pizza and ice cream, and that doesn't really make a lot of sense to do. And in this scenario, we will use either a histogram or a frequency polygon, which is basically the exact same as a bar graph or a line graph, except for we've done it by grouping data. When we draw histograms, we'll typically push the bars squished together and touching to indicate that it's a histogram rather than a bar graph. It's a very slight distinction, but it does exist. Let's go through an example here of grouping data and creating a graph. We've got the height of a bunch of different male semi-professional soccer players, and there's a lot of data here. We want to construct a histogram and frequency polygon for this data. Now, the first thing we're going to do is we're going to create a frequency table. So we'll say height, frequency, and we have to decide if we want to do frequency or relative frequency. I think it's going to make more sense in this scenario to do relative frequency. We're not going to fill in the cumulative relative frequency here because it doesn't really make sense to talk about that for the purpose of this graph. I would rather have a bar for each category rather than a bar indicating everything up to that category. Now, 100 different pieces of data. It looks like I'm going by every half inch based on this data. I have to decide how I'm going to group it. Now, in terms of the way it's printed, we can see that they've already indicated a way that they might like us to group it, which is they've grouped it by 2-inch segments. So this first category is 60 to 62. And then the next one looks like it's 62 up to 64, and so on, and so forth. And so that makes sense to group it. We're not going to write these exact measurements, though, because in this scenario, it's between 60 and 62, but I'm not including 62. I am including 60. This is particularly important because notice, for example, all of these 66s, and there's a lot of 66s. They were included in the 66 to 68 clump, not the 64 to 66 clump. So it's important that we note whether something that's on the boundary is on the upper end or the lower end. And a very easy way to do this is just simply move the boundary a little bit. For example, let's, instead of saying from 60 to 62, let's say it's going to be from 59.75 to 61.75. Because we measured to the nearest half inch, there's never going to be any 0.75s collected. And so this will make it very obvious where each data point is supposed to go. And this will allow us to fill in our different categories. So we're going to do 61.75 to 63.75, 63 to 65, 65 to 67, 67 to 69, 69, 71, 71 to 73. And we do have to go one more because there's a single 74. So 73 to 75. Now we can go ahead and count how many there are. So for the first group, we're looking here, 1, 2, 3, 4, 5 data points. It told us that there was 100 total data, so we know the relative frequency will be 5 out of 100, or 5%. We'll just put the percents from now on. For the next group, looks like 1, 2, 3 data points, or 3%. The next group is big, and actually, the next group is all the way up through here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 40 data points here. Next, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hang on 1 second. I think, did we miss a category? We may have missed one category. We did miss one category. This 40, we've skipped this category here, so we'll scoot everything down. This one is the 12. This one is the 17. This one is the 40. And the one we've missed was the 64 to 66 range. Up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So there's 15 here. Let's adjust the relative frequencies to match. 15, 40, 17, 12. Okay. Then here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again. 1, 2, 3, 4, 5, 6, 7. Oh, whoops, that was the same 12 we had already done. So then this one is the 7. And finally, this one is 1. I'll leave it for you to check on your own and make sure these all add up to 100. Assuming I counted everything correctly, they did. I may have miscounted one of these categories, but it's still good enough for us to create our graph, even if there's a small mistake. What we're going to do is we're going to create the histogram. So we'll label again. So this will be height in inches of soccer players. So down here we'll have height in inches, and over here we'll have relative frequency. Now we have to choose a good scale for this graph. The highest value I see is this 40. So I think it makes a lot of sense to put 40% up here, which means we might have bars that are 10%. So 10, 20, and 30. And then we can put little axis marks in between. We don't need to put the numbers there, but it'll help us guide our graph. And so let's count how many categories we have. 1, 2, 3, 4, 5, 6, 7, 8 different groups of data. So we'll split this into 8. And then we'll label them. So this one will be, we can put just the endpoints here. 5975, 6175, 6375, 6575, 67, 69, 71, 73, and then 75. And then we just go ahead and make each bar. So there's going to be our 5, We've got a 3. Notice how I'm squishing the bars really nicely together. 15. Then 40. This will be the big tall bar. 17, about here. I don't really care when you're drawing your graphs how nicely to scale they are, as long as they're close and you label things. 12, then 7, and then 1. And this tells a really great story. Looks like most of them are clumped towards the center in this range, kind of like the 64 to 70-ish range. And it looks like there's very few that are particularly short, whereas there's more that are particularly tall. The reason that we squish the bars together is because this data is nice and continuous here. And so we're kind of can even think about connecting a smooth curve that goes all the way. This curve doesn't actually exist because we didn't gather all of these data points in between for it to be so smooth, but it kind of tells a smooth picture. And we could create the exact same frequency polygon by just simply plotting these dots and connecting it with lines. In this scenario, I like the histogram better because it doesn't look like we're trying to show some kind of trend, but a frequency polygon could be a decent case here. I don't think either choice is much stronger than the other one. I would personally do a histogram, but I think a frequency polygon would be fine. That's all we've got for today. We'll see you guys next time.